Welcome to Mythosium, the channel where we take scientific ideas that often seem mysterious, confusing, or paradoxical, and turn them into clear, intuitive stories that actually make sense. Today we're exploring a topic that seems so straightforward at first glance that most people never question it. The speed of light, a number so famous that it's printed in textbooks, repeated in science documentaries, and embedded in some of the most fundamental equations in physics. 300 million meters per second. A cosmic speed limit that shapes the universe. But beneath this familiar number hides a profound puzzle. Even though the speed of light is one of the most carefully measured quantities in all of science, there is a specific measurement that no one has ever performed. And according to our best understanding of physics, no one can. It's not because our tools aren't good enough. It's not because light is too fast to chase. It's because the question itself touches a deep structure of space-time that prevents us from accessing the answer. To understand why, we need to look at what measuring speed really means. Whenever you measure the speed of something, whether it's a running person, a car on a highway, a sound wave, or a beam of light, you're doing the same thing. You measure how far it traveled and how long it took to get there, distance divided by time. But to do that for something moving in only one direction, you need two clocks, one at the starting point, one at the destination. And those clocks need to be synchronized perfectly. This seems trivial. Why would synchronizing two clocks be difficult? We synchronize clocks all the time. Phones, computers, servers, satellites. But these everyday examples rely on signals, radio, GPS, network pings, traveling between clocks. And those signals travel at the speed of light. So even before we start, we are already assuming something about how fast light travels. Our entire system of timekeeping is built on conventions that silently assume the very thing we think we're measuring. Imagine you try to synchronize two clocks by sending a pulse of light from one to the other. You tell clock B, when the pulse arrives, set your time to match clock A plus the travel time. But how do you know the travel time? You have to assume the light takes the same amount of time to go one way as it does to return. And that assumption, that symmetry, is not something we've ever measured. It's something we choose, a convention. This is where Einstein's insight becomes essential. He realized that simultaneity, the idea that two distant events occur at the same time, is not an absolute truth. It depends on the observer's motion. Two events that look simultaneous to one observer may not look simultaneous to another. Once you accept that time itself is not universal, but shaped by motion and position, you see why synchronizing distant clocks is not just a technical challenge, but a conceptual one. Einstein proposed a rule: define clocks as synchronized if light takes the same amount of time to go in each direction. This rule is not proven, it's adopted. It makes the laws of physics look symmetrical and elegant, it simplifies the mathematics, and it supports the idea that the speed of light is the same in all directions. But that symmetry is a definition, not a measurement. This means that the one-way speed of light, how fast light travels from point A to point B without returning, cannot be measured without making assumptions that already contain the answer. Every experiment ever attempted to capture the one-way speed runs into the same loop. You need synchronized clocks. To synchronize clocks, you need signals, and signals rely on the speed of light. This makes the measurement circular. You might think, what if we use something slower, like sound or mechanical movement, to synchronize the clocks? But sound waves need time to travel, and to measure that time, you again need synchronized clocks. A mechanical method, say carrying one clock slowly across the distance, introduces relativity's time dilation. Any acceleration or change in gravitational field affects the clock's rate. So even if you try to move it gently, the process introduces tiny shifts that you must correct for. And those corrections rely on the speed of light. Once again, the loop closes. This is why we can measure only the round-trip speed of light with complete confidence. If a beam of light travels from point A to point B and bounces back to point A, one clock is enough. You start the timer when the pulse leaves and stop when it returns. The round-trip time gives you the average speed. Countless experiments have confirmed that this round-trip speed is a constant. But how fast the light moved on the outbound leg versus the return leg is invisible to us. The idea that the one-way speed might differ in different directions may sound bizarre, but mathematically, physics still works even if the speed of light is faster in one direction and slower in the opposite direction, as long as the average remains constant. Einstein's equations, Maxwell's equations, and the structure of space-time all remain internally consistent under these different conventions. This shows that the symmetry we assume is not demanded by experiment, but chosen because it gives us a simpler and more beautiful picture of the world. One of the most startling consequences of this idea is that the speed of light is not merely a property of light. It is woven into the relationship between space and time. In the same way that the size of a foot or a meter rest on a definition, the speed of light is a constant that underpins the structure of space-time itself. Light isn't just moving through space, it is defining what space and time even mean. This conceptual shift was so profound that scientists eventually redefined the meter in terms of the speed of light. Rather than measuring how fast light travels over a known distance, distance is defined by how far light travels in a given amount of time. This makes the speed of light exact by definition, not because of measurement precision, but because it is part of the foundation of the universe's geometry. Given the structure, you might wonder whether any experiment could ever reveal differences in the one-way speed of light, maybe using extremely precise atomic clocks, quantum entanglement, or some clever asymmetric setup. But quantum entanglement cannot transmit information faster than light, so it cannot help synchronize clocks beyond the conventional limit, and asymmetric apparatuses all require calibration that again depends on the speed of the signals used in the calibration. No matter how advanced the technology becomes, any method that relies on communication or motion between two locations inherits the same synchronization problem. The impossibility of measuring the one-way speed of light doesn't mean the universe hides some secret speed that we're missing. Instead, it reveals something deeper. The laws of physics only require the round-trip speed to be consistent. Everything else is a matter of convention. The geometry of space-time, the transformations of relativity, and the consistency of physical laws depend on that round-trip constant. They do not depend on the one-way speed at all. You might think that if the one-way speed were different in different directions, we would at least notice something strange. Maybe distortions, delays, asymmetries in observations. But all of our instruments, clocks, and methods rely on the same conventions. They all agree with each other because they're built on the same synchronization rules. Even GPS satellites use a carefully defined convention for simultaneity that ensures all signals remain consistent. The system works because everything uses the same framework, not because we have independently verified the one-way speed. This leads to a philosophical but scientifically grounded realization. Some aspects of reality are not determined by measurement, but by the structure of the laws themselves. In the case of light, what we can measure is the two-way speed, and from that we build the definitions that make modern physics possible. The round-trip speed is not just a convenience, it is the invariant quantity that ensures causality, keeps signals consistent, and defines the structure of spacetime. It tells us how information can flow, how events are related, and what limits nature imposes. The one-way speed, on the other hand, sits outside the reach of experiment. It is a degree of freedom in how we choose to coordinate time across space. It is part of the language we use to describe the universe, not something the universe reveals directly. Understanding this changes how we think about measurement, observation, and even truth in physics. Not everything that seems measurable is actually accessible. Sometimes the limits are technological. But sometimes, like in this case, the limits are conceptual. They are baked into the nature of time, space, and causality. They tell us that some questions cannot be answered because they depend on definitions rather than independent physical facts. At Mythosium, we love exploring these subtle but profound distinctions, where everyday intuition breaks down and the deeper structure of the universe becomes visible. The speed of light is not just a number. It is a window into the geometry of reality. And the fact that we cannot measure its one-way value isn't a failure. It's a sign that our universe is more elegant and more constrained than it first appears. If you enjoy exploring these hidden layers of physics, the paradoxes that turn into insights, and the concepts that reshape how we think about the world, make sure to subscribe. There are countless mysteries left to explore, and each one brings us closer to understanding the remarkable structure of the cosmos. Thanks for watching, and stay curious.